So this is the walkthrough for the practice quest on balancing and classifying equations. So we're going to balance some chemical equations and classify them as to what type they are. So the first thing we're going to do is balance the equation, and to do that we need to count up the elements on both sides. So on this side we have 1 silicon and we have 8 sulfurs. On the other side we have 2 silicons and we have 4 sulfurs. So since the number of sulfurs is 8 on the left and 4 on the right, and we can't make the 8 any smaller, we can double the number on the right, and that makes this 8. The 2 in our coefficient here also applies to the silicon, and so that gives us 4, which means if we go back over here and we put a 4 in front of that silicon, we get 4 silicons on the left, 4 on the right, 8 sulfurs on the left, 8 on the right. That is balanced. As for the type of reaction, we have 2 reactants and we have 1 product. Anytime you have 2 reactants in a single product, that means you have a synthesis reaction. So 2 reactants, 1 product is always synthesis. Okay, here's the next one. So the line for this one is right here. Always draw the line at the arrow that separates the reactants from the products. So we have 1 mercury. On the left hand side we have 2 oxygens here. On the on the left hand side we have 2 hydrogens here plus another 3 here. That gives us 5. And we have PO4. We could break that up and count it as 1 phosphorus and 4 oxygens, but since we also have PO4 on our right hand side as a unit, I'm going to stick that as one thing, and I'm going to say there's 1 PO4 over here and there are 2 PO4s over here on the right. And then to tally up the rest of the right hand side, we've got 3 mercuries, we have 1 oxygen, and we have 2 hydrogens. So the first thing I will probably do here is, since we have mercury on the left and the right with different numbers, I can put a 3 there, and what that does is it changes my mercury number up to 3, which balances that. That 3 also multiplies the numbers that I have in parentheses here, so that gives me a total of 6 oxygens. It gives me 6 hydrogens there plus another 3, so that's 8 altogether. And then if I take a look at the phosphate, remember I have 2 over here and 1 over here, so if I double this number, that gives me 2 phosphates on the left. I have to recount the hydrogens though, because I changed that too. So I've got 2 times 3 hydrogens here, that's 6. I've got 3 times 2 hydrogens over here, that's a total of 12. So now I've got the hydrogens and the mercury, the mercuries and the phosphates are balanced. The hydrogens and the oxygens aren't, but since I have 12 hydrogens on the left, if I put a 6 in front of H2O, 6 times 2, 12 hydrogens, 6 times 1 oxygen is 6, and so that works it out so that now I have the same numbers of all these things on both sides, so it's balanced. This type of reaction, we have 1, 2 compounds on the left, 1, 2 compounds on the right where the parts have traded places, so that is going to be called a double replacement reaction. Double replacement is when you have 2 compounds on both sides, so double replacement is the type of reaction here. Okay, so first of all, for the type, we'll get that out of the way. When you have oxygen as a reactant, that's going to be called combustion. Okay, so anytime oxygen is one of the things on the left, O2, that's going to be a combustion reaction. So if I divide this one up, this one's going to be a little bit tricky. This is one of the times when the numbers are going to be a little bigger than you might think. So let's count this up. We've got 7 carbons, 6 hydrogens, and a total of 4 oxygens, because there's 2 in the first thing and 2 in the second thing, the O2. And then on the other side, I've got just 1 carbon, I've got 2 hydrogens, and I've got 3 oxygens. Okay, so the first thing I would try is obviously to put the 7 in front of the carbon. That makes that 7. Also makes this, the 7 times O2 is 14 plus 1 more, that'd be 15 oxygens. I still have 2 hydrogens here, I haven't changed that yet. Now the problem you're going to run into here is that I end up with an odd number of oxygens because I've got 6 hydrogens on the left, 2 on the right, so the first thing I'm going to try is to put a 3 there. Well, that gives me 14 oxygens in the first part plus 3 more in the H2O. That's 17. That's an odd number. No matter what I do to the left-hand side, I cannot make O2 and O2 come out as an odd number. So I'm going to stop here because I know no numbers I use on the left are going to work as is. So whenever you get to this point where you've got an odd number on one side and an even number on the other that you can't make odd because it's all, you know, a 2 or whatever, the next thing to do is to double the numbers you've got. So I'm going to erase the 7 and the 3, and I'm going to double them to 14 and 6. Now I told you the numbers usually don't get up above 10, but sometimes they do. So in this case they're going to be above 10. So 14 CO2s gives me 14 carbons over here. 6 hydrogens gives me 6 H2Os gives me 12 hydrogens. And then I've got 14 times O2 here, that's 28, plus 6 times oxygen is a total of 34 oxygens on the right side now. Now I've got to go back to the left and fix what I've done. So I had 14 carbons, I've got 7 now on the left, so I double that, gives me 14. Doubling that also gives me 12 hydrogen, so that works out. Now I've got to add up the oxygens. So far I've got 2 times 2, which is 4, plus 2 more, which is 6. I need 34. So I've already got 4 here. So if I put a 15 in front of the oxygen, 15 times O2 would be 30, plus the 4 in the first compound. That gives me 34 oxygens. So just to sort of clean out the arrows here so you can see, we've got 2, 15, 14, and 6 as our coefficients, and that's, again, a combustion reaction. Okay, so here again we've got O2 as a reactant, combustion, just to get that taken care of. Divide this up, and we've got 4 carbons, we've got 10 hydrogens, we've got 2 oxygens on the left, on the right we've got 1 carbon, we've got 2 hydrogens, and we've got a total of 3 oxygens. So already again I can see that I've got this situation where I've got CO2 and H2O, which makes for an odd number, and the number that I would want to put in front of the water to begin with, since this is H10, would be a 5. Well, 5 in front of the H2O is going to give me an odd number of hydrogen. An odd number of oxygen, right? So because it's going to be 5 times the O here plus the 2 there, it's an odd number. So I'm going to go ahead and I'm going to start by doubling what I would normally start with to make this an even number. So let me take my 5 and make that a 10. Let's see if that works out. So by making that a 10, I end up with 20 hydrogens, and so far I've got 10 times 0, or 10 times 1, which is 10 plus 2 more, that's 12 oxygens. Okay, so I've got 20 hydrogens on the left, on the right. I've got 10 on the left, so I'm going to double that, which gives me 8 carbons, gives me 20 hydrogens. And now I'm going to have to make this an 8, right, which gives me 8 carbons. Now I've increased the number of oxygens again, so 8 times 2 is 16, 10 times 1 is 20, 10 times 1 is 10, so that's 26 oxygens that I've got. I can go back over here, O2 times 13 would give me 26 oxygens. So that's balanced combustion reaction. Last one, we've got ammonia breaking up into nitrogen and hydrogen gas. When you have one reactant that breaks up into multiple products, that's called a decomposition reaction. Decomposition, which is the opposite of synthesis. Decomposition. Okay, decomposition reaction is when you have one reactant that breaks up into multiple products. So, 1 nitrogen, 3 hydrogen, 2 nitrogen, 2 hydrogen. Alright, I've got an odd number of hydrogens on the left that can never be even just that way, so I'm going to start by doubling. Gives me 6. Also gives me 2 nitrogens, so that actually balanced the nitrogens. And then if I put a 3 in front of the H2, that gives me 6 hydrogens, so hydrogens are balanced, nitrogens are balanced. Decomposition is the type of reaction. And last one, the type. We have an element by itself and a compound on the left. We have a different element by itself and a different element in the compound on the right. This is called single replacement. So the difference between double replacement and single replacement is that double replacement involves 2 compounds, whereas single replacement involves an element and a compound on each side of the equation. Usually in these equations, you're going to see the element that's by itself is a metal. It's not always, but that's very typical. So aluminum on one side, iron on the other. That would be something typical to look for a single replacement reaction. Now to balance. Aluminum, there's 1. Iron, there's 1. Chlorine, there are 2. On the left, on the right, I've got 1 aluminum, I've got 3 chlorines, and I've got 1 iron. So the aluminum and the iron are actually already balanced, but the problem is the chlorine's not balanced, so I'm going to have to fix that. So I've got 2 on the left, 3 on the right. One's even, one's odd. The smallest number they both go into is 6. So by putting a 3 there and a 2 there, gives me 6 chlorines on both sides. Balance the chlorines. 3 in front of FeCl2 means I've got 3 irons. So I'm going to put a 3 over here. Gives me 3 irons on both sides. A 2 in front of the AlCl3 means I've got 2 aluminums. So I go back and I put a 2 in front of that. It gives me 2 aluminums. So 2, 3, 2, 3 are your coefficients. The equation's balanced, and that's a single replacement reaction. Okay, so word problems, and don't forget the Brinklehoffs. We may or may not have talked about this in class, but the Brinklehoffs, these are the elements: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. These elements always come in pairs when they're on their own, which sounds like an oxymoron. But so if you have bromine in an equation or in a word problem, it says bromine reacts with. Bromine in the equation is always going to be Br2, never just Br by itself. It might be part of a compound and be HBr with just one bromine, but bromine as an element always comes in pairs. And the same goes for all these other elements. So iodine is I2, nitrogen is N2, oxygen is O2, etc. And so if you remember Brinklehoff, bromine, iodine, nitrogen, chlorine, H is for hydrogen, oxygen, fluorine, Brinklehoff, any of those elements as individual reactants are going to be diatomic, they're called. So Br2, I2, N2, and so on. Okay, calcium nitride reacts with sodium oxide to form calcium oxide and sodium nitride. So we're going to write the reaction, make it balanced, and identify the classification of the reaction. So calcium nitride, the ions are given to you here, and you just have to think back. Remember that the charges have to cancel out. The simplest way to do that is to swap the numbers. So calcium nitride would be Ca3N2, reacts with sodium oxide, and since oxygen's a +2 and sodium's a -1, we switch the numbers. And then we're going to have calcium oxide, which is just CaO, and sodium nitride, which is Na3N. I ran out of room there. So to balance, I have 2 sodiums on the left. I want to have 2 times 3 gives me 6 sodiums. 3 times 2 on the left gives me 6 sodiums on both sides. So sodium is now 6 after I add those coefficients. The calcium is 3 on the left, and it's 1 on the right. So I'm going to put a 3 here. That gives me 3 calciums on both sides. The nitrogen is 2 on the left, and because I've already put a 2 over here, I've got 2 nitrogens on the right. Oxygen, I've put a 3 in front of this compound, which gives me 3 oxygens. Got a 3 in front of this compound, which gives me 3 oxygens. So those are all balanced now. So the coefficients are 1, 3, 3, and 2. The type of reaction, I have 2 compounds on the left, 2 different compounds on the right. When you have that set up, it's going to be a double replacement reaction is the type. Iron 3 sulfide reacts with calcium, just the element, to form calcium sulfide and iron as an element. So to write this out, we're going to switch the charges around. So iron with sulfur is Fe2S3 plus calcium. There should be calcium with an A. Reacts to form calcium sulfide, which is just CaS, and iron, which is Fe. So Fe2S3 calcium 1. And on the other side, we've got calcium 1, sulfur 1, iron 1. All right, so I need a 2 in front of this iron, makes that 2. I'm going to need a 3 in front of the sulfur to make that 3. Putting that 3 in front of the calcium sulfide also makes the calcium 3, which means then in order to make this a 3, I've got to put a 3 in front of that. So 1, 3, 3, 2 are the coefficients in order. In this reaction, we have one element and a compound on the left-hand side. Those 2 elements trade places. So we have a different element and a different compound on the right. That is a single replacement reaction. So again, replacement. So the difference between the double replacement has 2 compounds on each side, 1, 2, 1, 2, whereas the single replacement has a compound and an element on one side and a different compound and a different element on the other side. Okay, nitrogen gas combines with chlorine gas to become nitrogen trichloride. So nitrogen and chlorine are both part of that Brinklehoff, right? Brinklehoff ClHOF. So in this case, we've got actually the two in the middle, nitrogen and chlorine, which means when you write them in the formula, it's N2 and Cl2, and the product nitrogen trichloride means NCl3. So nitrogen 2, chlorine has 2. On this side, 1 nitrogen and 3 chlorines. So I'm going to have to balance this by putting, since I've got 2 chlorines on the left and 3 on the right, we've got the even-odd situation. The smallest number they both go into is 6. So if I put a 3 in front of it on the left, and if I put a 2 in front of it on the right, then that will give me 6 chlorines on both sides. And since I put a 2 in front of this nitrogen, that gives me 2 nitrogens on the right, and I already have 2 on the left, so that's good. This reaction has 2 reactants, 1 product. Anytime you have 2 reactants and 1 product, you are talking about a synthesis reaction. Synthesis means combining. So when you have multiple reactants and only 1 product, it's called a synthesis reaction. Alright, so balance and a particle diagram. So to balance this, since I have nitrate on both sides, that's NO3, nitrate, I don't need to count up the nitrogens and the oxygens individually since they appear together on both sides. So with that in mind, the little numbers in the parentheses, or outside the parentheses I should say, are 2 and 3, even odd. So again, with 2 and 3, the smallest common multiple is 6. So I'm going to put a 3 in front of the copper nitrate. I'm going to put a 2 in front of the aluminum nitrate, which means I'm going to need to put a 2 in front of the aluminum on the left and a 3 in front of the copper on the right. So that balances it. This would be a single replacement reaction. And the particle diagram, what it's really asking you to draw is basically a rough idea of what the atoms are actually doing. So let's call those 2 aluminums. We'll say that copper is going to be blue. There's 3 copper nitrates. Okay, and obviously I know you can't color code necessarily on the test, but you can figure out another way to make them look a little bit different. And the NO3s we're going to make red. So there's 2 of those with each of the coppers. And then on the other side, we have 3 nitrates going with the aluminums. And then we have the copper. There's 3 of those. So really what the particle diagram is trying to show you is, if you look, there are 2 orange dots on the left and there are 2 orange dots on the right. So I haven't changed the actual number of atoms. And then the same with the red. There's 6 red circles on the left, there's 6 red circles on the right, even though they're arranged differently and connected to the aluminum instead of the copper. There's 3 blue dots, those are the copper atoms. There are 3 blue dots on both sides. So the particle diagram just sort of helps visualize the fact that we're talking about all the same building blocks that have just been rearranged and connected in different ways. So however you can show that on the test, that's fine, as long as each thing is somehow clearly defined, whether you fill one in, leave one blank, and make lines or an X in the other one or something like that, just to identify the different pieces that are being moved around. Okay, the net ionic equations are next. So this is when we have those double replacement reactions where you have 2 things in solutions, aqueous, and one of them becomes a solid on the right-hand side. That's called the precipitate. And so what's happening here is the ions, and I'm going to write out all the ions first, just again to show you, you don't have to do this necessarily on the test. This is sort of an intermediate step. Okay, break this up into ions, sodium ions, chloride ions. And then on the other side, we've got AgCl plus sodium ions plus nitrate ions. Okay, so all I did was I took all the things that were aqueous and separated the parts. So the silver is a part, the nitrate, sodium, the chloride. On the right-hand side, the sodium and the nitrate are the only parts that are still aqueous. So to write the net ionic equation, we're going to get rid of all the stuff that's aqueous on both sides. So we're going to get rid of this, and we're going to get rid of the sodium and the nitrate from both sides. So what we're left with in the final net ionic equation is Ag plus aqueous plus Cl minus aqueous produces silver chloride solid. So this is the net equation. This is what you're looking for. And we have another example that we can look at. So two aqueous solutions, one of the combinations becomes insoluble when they're mixed, which is the calcium carbonate. The sodium and the chloride are staying aqueous. So I'm going to eliminate the sodium. I'm going to eliminate the chloride. And so what we're left with is the calcium, which is a positive 2, and that's aqueous, and the carbonate, which is a minus 2, aqueous. And when they form a solid, they just go together, 1 and 1, calcium carbonate, solid. So there's the net ionic equation. Okay, so short answers, I'm not going to write all of these out, just sort of talk through them. But how does decomposition differ from synthesis? Well, decomposition and synthesis are the reverse of one another. Decomposition has something that breaks apart, whereas synthesis, so this is decomposition, this is synthesis. Synthesis is things getting together. So if you take the top one, flip it around, you get the bottom one. If you take synthesis and turn it around, you get decomposition, and vice versa. So decomposition is breaking apart a complicated reactant into simpler products, whereas a synthesis reaction is taking simpler reactants to form a more complex product. So however you can explain that in a sentence or two is what we're looking for. What has to happen for combustion reaction, and what are the common products? Well, for a synthesis reaction, and to identify a synthesis reaction, we're looking for O2 as a reactant. Okay, so O2 is one of the things on the left-hand side. Common products are CO2 and H2O. Now that's always the case when you have a hydrocarbon like propane, butane, methane, things like that. There are other combustion reactions that don't produce these things, but those are very common products of a combustion reaction. What is produced in a precipitation reaction? A precipitation reaction involves solutions as reactant, so dissolved ions, and the product is a solid. That's the precipitation reaction. There are other double replacement reactions with different types of products, but what we're talking about here with a precipitation reaction is a solid being produced. In a solution of FeCl3, iron chloride, what you really have is iron ions and chloride ions. In this case, it's a 3-to-1 ratio. So 1 iron 3 for every 3 chloride minus 1s are floating around in the solution. So you have separated ions that are surrounded by water molecules floating around separately in solutions. Precipitation reaction has these ions that don't form a compound, that we don't include in that net ionic equation. Those are called the spectator ions because they do not participate in the reaction. They're just kind of there watching. They're spectating. They're not actually doing anything. They're floating around as ions at the beginning. They're floating around as ions at the end, so we call them the spectators. So in the types of reactions lab, we had the hydrogen peroxide. You added the black powder, which is manganese dioxide. This little thing here should kind of be over the arrow. That's called a catalyst. A catalyst is a substance that helps a reaction to take place without actually being a part of the reaction. So the reason the manganese dioxide does not get written into the equation on either side, but it actually appears over the arrow, is that the manganese dioxide is not changed during the reaction. You put the manganese dioxide in, and when the reaction is all over, the manganese dioxide is still there. So a catalyst helps a reaction, and we'll talk later in the year about how that works, without being part of the reaction. So it doesn't get changed, the reaction. RXN, sorry, abbreviation for reaction. So a catalyst helps a reaction take place without actually being part of the reaction, which is why we don't include it as a reactant or a product, because it's unchanged. It's not something that's being changed from one substance into another. And finally, how does a balanced chemical equation demonstrate the law of conservation of mass? The number of atoms on both sides of the equation is the same. Okay, so law of conservation of mass says the total mass of the reactants equals the total mass of the products. That's what it actually says. What it means is that the number of atoms is the same from beginning to end. They are rearranged, different compounds are formed, but the number of atoms stays the same, which is why the mass stays the same, and the balanced equation shows that, because in order for it to be balanced, you have to have the same number of atoms of every element on both sides, even when they're rearranged. So that's how it supports the law of conservation of mass. And that is the end of the practice test walkthrough. So the quest will be coming up the next time we meet.